Hey there! Ever wondered what the deal is with a massive instant explosion versus the slow, steady creep of rust on a bike? They're both chemical reactions, right? But they're happening on completely different clocks. Well, today, we're diving deep into the science of chemical speed and figuring out how to master the rates of reaction. So yeah, you see magnesium burning in this brilliant, blinding flash. And then you have iron, which takes years to rust away. The huge difference between these two is exactly what we're talking about. Chemists call this the rate of reaction. It's basically a measure of how fast your starting ingredients, the reactants, get turned into your final stuff, the products. So how do we actually put a number on this speed? Well, we track how much the amount of a substance, its concentration, changes over a certain amount of time. You can think of it like a car's speed in miles per hour, but for chemistry. It's all about how much stuff changes per second or per minute. To pull this off, we have to watch for something we can actually measure. Maybe it's a gas filling up a syringe, or maybe a solution is changing color. We record these changes at set intervals, say every 10 seconds. Then we plot that data on a graph. And here's the really cool part. The steepness, or the gradient of that line, tells you exactly how fast the reaction is going. A super steep line means a super fast reaction. And as that line starts to flatten out, you know the reaction is slowing down. Okay, so we know how to measure the speed, but what is actually going on down at the molecular level that decides that speed? The answer to that lies in something called collision theory, and it's based on a really simple idea. For anything to react, the particles have to physically collide. But hold on, if it's all just about particles bumping into each other, why isn't everything around us just constantly reacting? I mean, think about it. Billions and billions of particles are colliding every single second, but most of them just bounce off each other like tiny billiard balls. So what makes a collision a successful one? It turns out there are two golden rules. First, they have to hit each other in just the right way. The orientation has to be perfect, kind of like a key fitting into a lock. And second, and this is the big one, they have to smash into each other with enough energy to actually break their old bonds. This minimum amount of energy needed has a name, and it's super important. It's called the activation energy. This brings up a really interesting question. We all kind of know intuitively that heating things up makes reactions go faster, right? But is that just because the particles are whizzing around and bumping into each other more often? Or is there something else going on that makes those collisions more effective? Let's find out. And that leads us perfectly into the four main factors, the four big levers, really, that we can pull to control the speed of a reaction and make it do what we want. So our first lever is temperature. When you crank up the heat, particles start zipping around like crazy. They've got way more energy, which means they're not just moving faster, they're colliding more often and with a whole lot more force. And boom, there's the answer to our question from a minute ago. A higher temperature doesn't just give you more collisions, it drastically improves the quality of those collisions. A much bigger chunk of the particles now have enough energy to get over that activation energy barrier we just talked about. So you get more collisions and more of them are successful. It's a total win-win for reaction speed. All right, next up, concentration. This one's pretty straightforward. Imagine you're in an empty room versus a really crowded room. Where are you more likely to bump into someone? The crowded room, obviously. It's the exact same idea with chemical particles. It's really just a numbers game. The more particles you cram into the same space, the more often they're going to run into each other. It's unavoidable. And since reactions depend on collisions, increasing the frequency of collisions is a surefire way to increase the reaction rate. Our third lever is surface area, and this one is super visual. Imagine you have a solid strip of magnesium and the exact same amount ground up into a fine powder. You drop them both in acid, and the powder just erupts in fizzing almost instantly. Why the dramatic difference? Well, a reaction can only happen where the two substances actually touch, on the surface. With a solid strip, only the atoms on the outside are in the game. But when you grind it into a powder, you expose all those millions of atoms that were trapped on the inside. You've just massively increased the available surface area, creating way more spots for collisions to happen all at once. And finally, our fourth, and maybe the coolest factor, the catalyst. A catalyst is like a chemical matchmaker. It jumps into the reaction, helps things along, speeds everything up dramatically, and then it just leaves at the end, totally unchanged. How on earth does it do that? Here's its secret. A catalyst doesn't give the particles more energy. What it does is offer an entirely different, much easier route for the reaction to take. A shortcut, really. A pathway that has a lower activation energy. It's like a mountain guide showing you a secret tunnel through the mountain, instead of making you climb all the way over the peak.
You know, that whole idea of an energy barrier, that activation energy, is really the master key that connects all four of these factors together. So let's visualize it. Think of it as an energy hill that every single reaction has to climb over to get to the other side.
You see, to get from reactants to products, molecules don't just magically transform. They first need a little push, an input of energy to start breaking their old chemical bonds. That initial energy barrier, that activation hill they have to climb, is the activation energy. We can actually map out this whole energy journey. For an exothermic reaction, you release energy, so the products end up at a lower energy level than where you started. For an endothermic one, you absorb energy, so the products are at a higher level. But look closely. Notice how in both cases, you still have to climb that activation energy hill just to get things going. And this is where we can really see the magic of a catalyst. When you add one, it creates a brand new path on our energy map, one with a much, much lower hill. The starting and ending points are exactly the same, but the journey itself just became way easier. This means a lot more molecules can make the trip in the same amount of time. So, this is all cool stuff, but why does controlling these energy hills and reaction speeds actually matter? Well, it turns out it's fundamental to pretty much all of modern life. Let's take one of the most important industrial processes on Earth, making ammonia for fertilizers. I mean, just look at these numbers. The scale of this is mind-blowing. We're talking tens of millions of tons every year. The thing is, the reaction to make ammonia is naturally incredibly slow. It's only possible to do it on an industrial scale because we use high pressures, high temperatures, and, most importantly, an iron catalyst to speed things up. Without controlling these rates, we literally couldn't produce enough fertilizer to feed the planet. Okay, let's do a lightning recap to lock this all in. For a reaction to happen, you need a collision with the right orientation and enough energy. We can control the speed with our four levers: temperature, concentration, surface area, and catalysts. Catalysts are our secret weapon. They provide a shortcut with a lower activation energy. And that activation energy is the ultimate gatekeeper, the energy you have to pay to get any reaction started. And really, that's the big takeaway here. Understanding chemical speed isn't just some abstract science problem. It's the key to making everything from life-saving medicines to the food on our plates. In fact, right now, inside every single cell in your body, tiny biological catalysts called enzymes are controlling the rates of reaction that are keeping you alive. This isn't just the science of speed, it's the science of life itself.